Hello guys, welcome back to my channel. Today I'm going to talk about the direct stiffness method or displacement method for structural analysis. And for this video, I only talk about the truss element. So the first thing is the degree of freedom. You can say that the degree of freedom is a number of independent displacement coordinate that we can use to define the form shape of structure. So you can look at the example here. We have a beam like this one. So if this beam deform to this one, you will need the information from 6 degree of freedom. So you will need the placement at this degree of freedom and rotation, and also at the end node of the beam here. So the total of the degree of freedom is equal to 6. So the next is direct stiffness method. You can look at the formula here. The P is the external force vector, and the U vector here is the deformation vector, or the vector that collects the displacement at degree of freedom. So to do the structural analysis by using the direct stiffness method, you can follow the step here. The first thing is you need to define the degree of freedom, and then you need to define the vector P and vector U. And the next step is you need to determine the stiffness matrix by using the constitutive law, compactability, and equilibrium. But I will not talk in detail about this part here, but I will show you how you can formulate the stiffness matrix in order to do the structural analysis. And the last step is we can find the internal force after we find the first 3 steps here. Okay, this is the example that I'm going to talk about by using this method. This is the axial stiffness of each element. So this is the axial stiffness of the element A and B, and the last one is C. Okay, so I'm going to start with the first step. So step 1, define degree of freedom. So I'm going to draw the structure again. Now we have a load here. So this is A, B and C. We have node number 1, 2 and 3. So next you can define the degree of freedom. So to define the degree of freedom, you need to start with the free degree of freedom first. and then end with the support degree of freedom. So what I mean is we have free degree of freedom and support degree of freedom. So I will define this as degree of freedom number 1, number 2, and then we will continue with the support degree of freedom. So this is 3, 4, 5, and the last one here 6. So this is the degree of freedom that we're going to use. Next we can define the force vector and the displacement vector. So P, we have 6 elements. We have 1, 2, 6. So you can look at the structure here. The external force at the degree of freedom number 1 is equal to 0. We don't have any force. So we have only the force at the degree of freedom number 2. So it will be 0, 10, 0, 0, and 0. And if you're looking at the direction of the external force and the degree of freedom, you will see that they are the same. So it will be a positive number. But if it is not, if they are not the same, you will need to change the sign here to negative. Next, the vector u. So we have 2 unknown displacement. The displacement at the degree of freedom number 1 and number 2. And for the other degree of freedoms, they are equal to 0 for the displacement, because it is the support, and we know that the displacement at the support is equal to 0. So this u1, u2, and 0, 0, and 0. So this is the vector u and vector p, and you can divide it like this in order to easy to do the calculation. And the first part is pf, and the last part is po, and this is uf and uo. So this is why we need to define the degree of freedom, start from free degree of freedom and end with support, because it's easy to collect the data in the vector like this, and we can divide it into 2 parts to make the calculation easier. So the next step is we're going to form the stiffness matrix. So step 3 is stiffness matrix. Okay, in order to define or determine the stiffness matrix, you need to know the local stiffness for each element. So you need to start from element A, B, and then the last one, C. And the formula that we're going to use to find the local stiffness is K. It is a small k. It indicates that it is a local stiffness. A here is the transformation vector. We need this transformation vector because we need to, for example, if a beam like this, we need to change the local coordinate to global coordinate. So we need this transformation vector to change the coordinate here, so that we can form the structural stiffness. And we know EA here from this, and L is the length of element. Okay, so for element A, we can draw element A. We have this degree of freedom that associate with the element A. So it will be 3, 4, 1, and 5. And for the transformation vector, you can define it. It is equal here. I will write it first, and then I can explain later. So this is the alpha. It is the angle of the element here. In this case, the alpha is equal to 0. So this is the transformation vector. So in order to define this, you need to define the direction of the element. So I'm going to put it here. It is important because you need to define the start point of the element and then the end point of the element. So A will equal to, you can look at the length here. So this will be Hj minus Hi over L, and this one is Yj minus Yi over L, and it's the same for the these two, they just have different sign. So you can find this value. This one will be 120 over 120. You can do this already. So this is the transformation with the A. So now you can find the local stiffness of this element. We get the EA from this one. The matrix here will be 4 by 4. So I already calculate this. So I'm going to put the number here. So we have find the local stiffness for element A, and you can do this for element B and C. It's basically the same step, but I want to remind you that for element B, it will be something like this. So first you can define the direction. This will be I and J, and then you put the degree of freedom. So it will be 1,5 and 6,2. And you can using the information and find the transformation vector, and then you can find the local stiffness of this element. For element C, it's also the same. So I will skip this calculation part. Okay, now we got all three local stiffness for each element. So we have Ka, Kb and Kc, and then we can form the global stiffness. Now we need to draw the element here. So this is element A, and this is element B and C, and you will need to put the degree of freedom for each element. So the first element will be 3, 4 and 1, 5. And for the second element, you can define here 1 5 and 2 6 and 2, and for the last element, and this is 3 4. So in order to form the global stiffness, you need to define the degree of freedom for each row here. So what I mean is, if you look at the element A here, the first degree of freedom is degree of freedom 3. So this will be 3 4 1 and 5, and for the row number it also like that, 3 4 1 and 5. And for the element B, it also the same. It starts with 1 5 6 and 2, 1 5 6 and 2, and also the same for the element C. I'm going to put the direction here. So the global stiffness will have the size 6 by 6, because we have total of 6 degrees of freedom. So will be 1 2 3 4 5 and 6, and 1 2 3 4 5 and 6. So for the number here, it is K11, this is K12, K13, and so on. Also the same for the row. Now to find the value K11, you need to do the summation. So this is the K11. We have K11 here, and for this matrix here, it doesn't have K11, so we don't have to take any number from this. So we only need the value here and here, and we can do the summation. So you can find the value K11. So at this case, it will be equal to 120.6, and you can do the same for K12, K13, and for the other value as well. So this is how you form the global stiffness. There are many ways to form the global stiffness easier than this method here, but I will only talk about this method because it's easy to understand and it is easy to do in easy to do when you do the programming for the structural analysis. For example, like if you want to use the Matlab or Python to do structural analysis, this method will be easy to do. Okay, so I will skip this part again in order to make this video as short as possible. Okay, now we got the global stiffness matrix. But what I want to tell you is that we can divide this stiffness matrix also. So I will divide it like this because we have two 3 degree of freedom and 4 support degree of freedom. So this is why again we need to define the degree of freedom, start with 3 degree of freedom and end with support degree of freedom, because it's easier to divide the matrix like this and make the calculation easier. So for the first part here, I will call this KFF, and for the second part here, this one is KFO, and this one is KRF, and for the last part here will be KRO. Okay, so we complete the step number 3. The next part is we can find the internal forces. So to find the internal forces, we need to find the unknown displacement first. So we have 2 unknown displacement, U1 and U2, and to find the unknown displacement you can use this formula. So we already know PF and KFF, so you can find the inverse matrix of KFF, and then you can do the multiplication of the matrix, and you can find the displacement at degree of freedom number 1 and number 2. So I will skip the calculation part and write the result here. So this is U1 and U2. Now to find the internal force you can use this formula. So A again is the transformation vector, and we already know the transformation vector from the step number 3 here, so we can use this information again to find the internal force. And small u here is the displacement, but it will only define the displacement for one element. So for example, this is the element A will be like this, and the degree of freedom will be 3, 4 and 1, 5. So u here will equal to it is a vector 4 by 1. So we start from degree of freedom numbers 3, 4, 1, and then the last one 5. So as you can see here, the placement at degree of freedom number 1 and number 2 has this value, but the other degree of freedom, the displacement at other degree of freedom are equal to 0. So for this vector it will equal to 0, and only the degree of freedom at number 1 here is equal to u1. So u1 is equal to this number. So this is the vector small u. Now you can take this vector and do the calculation here, and you can find the internal force. Again, I will not do the calculation. You can do it by yourself, but I will show you the result here. For the element A, the internal force is equal to minus 1.96, and B and C. So this is the result. And after you got this result, you can continue finding the reaction force. So the reaction force, for the reaction force, you can use formula here, and this information we already know it. So K or F is this matrix, and UF it is this vector. So this will be a matrix 4 by 2 multiplied by the vector 2 by 2. Sorry, I think I got this wrong. This is 2 by 1. So the result here will be the vector 4 by 2 by 1, and the result is the number here. You can do this calculation by yourself. So this is a column vector, but I put the transpose here in order to make it easy to write. So you got the internal force and now the reaction force. So this is how you can use the direct stiffness method or displacement method to find the internal force of the truss element. And remember that you can write a small program by using this method, and you can find the internal force easy and fast. So this is just a small example, but if there is a complex truss, a complex shape truss, it will be hard for the hand calculation. So that's why you need to make a small program by writing code. You can use Matlab or Python. It depends on you. You can use any other programming language, but this is the good method for doing something like that. I hope you get the idea, and this is the end for my video here. And if you have any question, you can write in the comment section below, and don't forget to subscribe and hit the notification bell so you won't miss the new video. And if you like this video, please put a thumb up as well. I will be grateful for that. Thank you so much for watching. I'll see you guys later.